Yes?
Yes, sir.
Good. So yesterday we introduced this relation on strings of symbols. Uh, so this relation is called single step derivation. And then we introduced zero or more steps of derivation by taking the reflexive transitive closure. But we also want to talk about two special cases of this reflexive transitive closure. Yes? Any questions? These are known as leftmost and rightmost derivations. In a leftmost derivation, you always replace the leftmost variable. In a derivation, you can pick any variable to replace, but in a leftmost derivation, you always pick, at every step, you always pick the leftmost variable. Right? And similarly, in rightmost derivation, always replace the rightmost variable, right? And these are denoted by writing LM, and similarly, yeah, LM. And these are RM. So these are just special types of derivations. And immediately we have the proposition that A derives, the variable A derives if and only if A derives W by a leftmost derivation. If and only if A derives W by rightmost derivation. So what this is saying is the order in which you replace the variables does not matter as long as you use the same production, the same right-hand side of a production to replace the variable, right? So yeah, the next definition is of a sentential form. So we say that alpha, which is a string of variables and terminals, is a sentential form if it can be derived in 0 or more steps from the start symbol. And similarly, we talk about leftmost and rightmost. Sentential forms in case S derives alpha using a leftmost derivation, or S derives alpha using a rightmost derivation. Okay. Now, parse trees. This is the most important, one of the more important concepts in the study of context-free languages. Okay. So we are given a grammar. A parse tree sometimes also called a derivation tree, of G is a tree satisfying the following conditions. Number one, each interior node is labeled by a variable. And by interior, we mean non-leaf. Okay. And each leaf is labeled by either a variable a terminal or epsilon. Okay. And there's a further condition. If the leaf is labeled by epsilon, then it must be the only child of its parent. Okay. And remember, for a variable a right arrow epsilon can be a production. So that's allowed. Number three, if an interior node is labeled by A, and its children are labeled by x1 to xk, I'm not assuming anything about these x's. Oh, sorry. Each x is a single symbol. So it can be either a variable or it can be a terminal. Or in a special case, it can be epsilon. Then there of course, k would be 1. Labeled by x1 to xk from the left. Then a right arrow x1 to xk is a production of G. Okay, so let's take an example. Before that, another definition: the yield of a parse tree this is simply the string obtained by concatenating the labels of the leaves from left to right. So you just read off the labels of the leaves from left to right. That is the yield. So here's an example. Let's go back to our grammar for palindromes. So this was the grammar, right? We have the empty string 0, 1, 0, S, 0, 1, S, 1. Yeah. Okay. So here's an example of a parse tree. You have S at the root. Okay. But that is not required. If you look at the definition carefully, it doesn't say that S has to appear at the root. So the root can be any variable. Okay. Right. So let me just confirm that. Yeah, it can be any variable. In this particular example, the root is S, okay? And at the next level, you have this. And at the next level, 1s1. So if you think about it, a parse tree is just a way of representing a derivation, okay, where the order in which you replace the variables is ignored, okay? So this is a parse tree. And one thing which is not mentioned in the definition, but which is important, is that this is an ordered tree, okay? So the children of any node are ordered from left to right. Okay, that order matters. Okay. So that is missing in the definition, right? But that is understood here. So any questions about a parse tree? And what is the yield? The yield is simply the, the concatenation of all the symbols appearing at the leaves. So that is 0, 1, 1, 0. Right? One more thing. The yield may have variables. It's not necessary that it has to have only non sorry, only terminal symbols, right? So the string obtained by concatenating the labels of the leaves, right? Because a leaf can be labeled by a variable, a terminal, or epsilon. Okay? It doesn't have to be, a leaf doesn't have to be necessarily labeled by a terminal or epsilon. It can also be labeled by a variable. Okay, so in this case, we have only terminals and epsilon, but that's not necessary. And similarly, at the root, you can have any variable. Okay, any doubts? Okay, so here's a theorem. So let G be a context-free grammar. VTP, VTSP, sorry. For any A, for any variable A, and alpha, a string of variables and terminals, A derives alpha in 0 or more steps if and only if there is a derivation, there is a parse tree with root labeled A, and yield alpha. So this theorem relates derivations and parse trees, okay? And because this is if and only if, you have to prove in both directions. So going from left to right, suppose you have a derivation, A going to alpha in 0 or more steps. How do you prove that there is a parse tree with a root labeled A and yield alpha? What will be the method
Induction on number of steps.
of the derivation? Right. So this is by induction on the number of steps of the derivation A going to alpha. Okay. And I'll not do the proof. It's an easy proof. Either do it yourself or read it from the book. Okay. What about the other way? Suppose you have a parse tree with root labeled A and yield alpha. Uh, how do you show that A derives alpha? What method will you use here? Well, as you can guess, you'll use induction, but here there seems to be a lot of choice. You can use induction on the number of nodes of the tree or the height of the tree. So actually what works best, or rather what works easily, in fact, it may be the only choice, but let's not go into that, is by induction on the number of internal nodes. K of the parse tree. Because if you think about it, let me just give a hint about the proof. When K equals 1, you have this situation, right? Sorry, I shouldn't draw those arrows. That's not what is done. Right? And then from the definition of a parse tree, we know that A goes to X1 to Xk must be a product because of this one. And suppose the theorem is true for all internal loads up to some K equals N, right? And then you want to show it for the number of internal loads K equals N plus 1, okay? This is strong induction, by the way. So you have to assume that the theorem is true for all values of K up to N. And then you show it for N plus 1. Then you assume that the root of the, well, we are given that the root of the tree is A, right? And uh, suppose it has some sorry, I'm confusing between 2k. Let me use n here. Here, suppose we are using n equals m plus 1, right? So assume the theorem is true for all values of n up to m, and then you need to show it for n plus 1. Then suppose these are the children of the root, and we know that they are either variables or terminals or epsilon. But because the number of internal nodes is n plus 1, not all of these xk's, uh, m of course is, not all of these xk's can be, xi's can be leaves, because that is the case for n equals 1, when all the xi's are leaves. So in this case, at least one of the xi's will be a non-leaf node. So uh, now we can apply the induction hypothesis to each of these subtrees, and some of them may be leaves, but there'll be at least one subtree which is not a single node, because we have already taken care of that here, right? And then you can show that A derives, assuming that the yield here is alpha 1, alpha 2, and alpha k, uh, because A derives x1 to xk, right? And each xi derives alpha 1, it is easy to show that you will have alpha 1, alpha k, right? Yeah. So that is just the outline of the proof. You need to work out the details. Okay. So these simple proofs I'll skip from now on. So what we can state about parse trees and derivations is, this is a summary, right? For a CFG, so to summarize, for a CFG G and a variable A, the following are equivalent. A derives W. A derives W by a leftmost derivation. A derives W by a rightmost derivation. And there is a parse tree with root A and yield W. So these are all equivalent. Okay. And this is the origin of the term context free. Why do we use this term context free? This is the reason. If X derives gamma, then for any alpha beta, it is also the case that alpha X beta derives alpha gamma beta. Okay. So it doesn't matter what the context of X is, what it is surrounded by, right? If X derives gamma, then anything which surrounds X will derive the string resulting from surrounding the yield gamma by the same context. Okay, so that's why we use the term context free. And there are other kind of grammars which are known as context sensitive, in which this does not hold. But we will not go into those things in this course. Any doubts or questions?
Sir, in this, is X a variable?
Yes, it is a variable, but this is true for any arbitrary string. Huh?
Okay, this thing will be true if even if we have X as a string.
Right.
Oh, okay, sir.
Yeah, yeah. Because that follows from this statement itself. Yeah. Okay. Any other doubts? So we are using certain convention. These alpha, beta, gamma, these are strings of variables and terminals. This is a convention. And A, B, capital A, B, C, S, these are variables, of course. But X, we have been using for a single symbol, at least in this proof. X was a single symbol, whether epsilon, it could be epsilon also in this case, or a variable or a terminal. Okay. So depending on the context, right? But here we really meant a variable. Okay. Okay. the next important concept. This is known as ambiguity. Okay. So as an example, take the grammar for, maybe I should write CFG for the grammar for arithmetic expressions. Right? And consider the sentential form. It is actually a by the way, sentential form, as we said, is where is it? Is a string of variables and terminals, which is derivable from the start symbol S, right? But a sentence is just a string of terminals, which is derivable from S. That's called a sentence, okay? So the example we have taken is actually a sentence, right? Because it has, sorry, we have not written the example, A plus B star A. So this is a sentence because it has all terminals, right? In the convention, the small letters will these will be terminal symbols. Okay, so this is. So consider this sentential form, and there are two different parse trees, well, at least two different ones, for this sentential form as the yield. So we could have, I'm sure you have come across this phenomenon earlier, ambiguity, right? So, I mean, this is really talking about which operation has more precedence and things like that. So do we parse it as A plus B star A or A plus B star A? So that is the question. The grammar itself doesn't tell us how to do that, because both these parse trees are possible. And right? So these are two different parse trees. So that leads us to the definition of ambiguity. We say that a grammar a CFG G is ambiguous if there is a string W belonging to T star for which there are two different parse trees. So we are talking about a sentence here, but anyway, for which two different parse trees, meaning two parse trees with the same yield, two different parse trees. Okay. Any doubts about this definition? And remember, we are talking about the grammar being ambiguous. And I have not described, I described this grammar in the last class, but if you remember, we had productions from E to E plus E, as well as E star E. And of course, other things like ID and so on, right? I'm not writing them again. So for the same string, we have two different parse trees. That's called ambiguity. The grammar is ambiguous, right? Now, this does not mean that there are two different derivations for the same string. It's much stronger than that, because if you change the order in which you replace a variable, you get two different variables. For example, the leftmost and the rightmost derivation of a string will be different. But that doesn't mean that the grammar is ambiguous, because the parse tree can be the same, right? So this is different from there being more than one derivation of the same string. In general, there'll be many derivations of the same string, depending on the order in which you replace the variables by some right-hand side of a production. But this is different, okay? So please understand that. So another way of saying it is if there are two different leftmost derivations, for the same string, then the grammar is ambiguous. Or rightmost derivation, two different rightmost derivations, okay? Now, in many cases, we can remove the ambiguity, okay? And I'm sure you've come across how to remove the ambiguity for this grammar for arithmetic expressions, right? So some somehow we reintroduce precedence of operator, right? To remove the ambiguity. And to do that, we introduce some new variables, right? I would remain exactly as it was. Identifiers are the same, and so are the numbers. No change there. N0, N1, minus N plus N. But now we introduce two new variables called factor and term, right? So a factor is either an identifier or a number or an expression in parentheses, and a term is either a factor or uh, T star F, which really means that a term is a product of factors, because somehow we are, I mean, this is really like using recursion. If you think about this, these last two productions for T, we are using recursion. So we are defining a term as a product of factors. And finally, an expression itself is a sum of terms. Okay. So by doing this, we are implicitly assigning higher priority to multiplication, right? So multiplication would bind tighter than addition. Okay. If we do this, so to explain this, these factors are cannot be broken apart by operations, whereas these terms that can be can be broken apart only by star. And this is the set of all expressions. Effectively saying the same thing, which I mentioned earlier. So if you do that, what would the parse tree for this expression look like? A plus B star A. And how many parse trees do we have? Well, we must have E at the root, right? Now, there are two possibilities because there are two productions for E, either T or E plus T. So which one do you think we should use?
E plus T.
And why? Because if we use this production, right?
Then it cannot be broken by just a star.
Right. So after this, we have a choice, either F or T star F, right? In both cases, we will not be able to take account of this plus, okay? So this will not work. T star F will not work because then we'll have to somehow derive A from here, and star, of course, is a terminal, and A plus B. This is not possible, right? This is not possible because T can only derive uh, product of factors. It cannot derive sum, right? On the other hand, if we use the other choice, what would happen? There's no way to make progress, right? Because the only choices for F are IN and left parenthesis E, right parenthesis. And none of these match this expression. So this is not possible, okay? So the only way to parse this expression is to use E plus T, right? Let me bring down, yeah. Then, well, we have matched the plus. So we know that this is the only choice. There's no choice here, okay? So this will be F I, right? F goes to I, B, this is F, I, A, right? And E goes to T, goes to F, goes to I, and this goes to A. Okay, so you've got it. Of course, this doesn't prove that this grammar is unambiguous. Yeah, but we are not going to prove it. I'm not sure it's there in the book. Not sure about that. But we are not going to prove it. Okay. Okay, so we have reached the end of our class today. If you have any questions, let me take them now. There'll be a quiz on Monday, and I'll let you know the details by Teams, through Teams, and by email. Any doubts? Okay, let's call it a day.